Hi everyone, on this next increment of videos, I'm going to be discussing section 3.9. So I'm going to break this up into several different videos just because section 3.9 contains a lot of word problems, they're pretty lengthy, and then if you're listening to the lecture, you might want to split it up into pieces too. So usually when I teach this in class, I'll do some examples and a little bit of lecture, and then I'll let the students work together and bounce back and forth just because it is kind of a long lecture. So just keep that in mind as you're kind of planning to go through notes. You might not want to sit through the whole thing at once. So with that, I'm going to break the videos up, but one thing that I want to discuss, which I think I've mentioned before, is that for most students, 3.9 is the hardest section in the course. So I would say it's kind of a toss-up in between 3.9 and 4.7 because they're both fairly complex word problems and story problems. But section 3.9 is about related rates. And so when we were in section 3.7, we just had rates. So everything that we took the derivative of was with respect to one variable. So, maybe we had an equation of y in terms of x, and obviously you saw there are more complex things than that, but we were still differentiating in terms of one variable. Here we're going to have to use that concept of implicit differentiation. So where related rates comes from is the idea that usually things in real life that we model aren't necessarily as simple as just one cause and one effect. There are things that kind of intertwine, and so you have to think, okay, well, if this happens, how is this going to impact this and this and this? And the thing is, as those things change, they have a rate of change. And so if one thing changes or it has a rate of change, then the other thing has to change too. So this puts that together. Like I said, this will be tough. It's going to take a lot of prerequisite skills. I think that is part of the thing. That's actually the toughest. But keep in mind, there have been many students before you that have gone through it. Lots of real smart people who came up with the concept in the first place. So you can do it. Just know it's going to take a lot of work. This is not something you're going to be able to kind of procrastinate on and just tackle, a couple hours before it's due. It's really going to take some time, but be sure to work at it. Okay, so let's switch this over and get into the actual notes. All right, first thing, like I just discussed, let's recall that derivatives really tell us about rates of change. And so like in 3.7, we're going to look at this in multiple different contexts. So for example, let's say a dose D of a drug, and that should be drug without an E, of course. Okay, so a dose D of a drug causes temperature changes T in a patient. If C is a positive constant, and we're given the equation T equals C over D minus D over 3 times D cubed, what is the rate of temperature with respect to dosage? Okay, so similar to what we looked at in section 3.7, I know that I'm looking at trying to find the rate of change of temperature. So we know we want the rate of change of temperature would be dt, and it says with respect to dosage. So we should remember that what that really means is we have a dd at the bottom. Okay, so our goal is to try to find dt dd. All right. I am going to just rewrite this equation so it's a little bit easier to work with. So first, let's keep in mind that c over 2 is really just some constant because c was given as a constant, and I'm going to distribute the d cubed through. So I'd have c over 2 times d cubed minus d times d cubed is d to the 4th, and I'm just going to write this as a 1/3 times d to the 4th rather than writing it over 3, although those are the same thing, so it really doesn't matter. Okay, so if I'm looking at what I have, this actually looks pretty nice, and it's more gentle than some of our questions will be, and that's because if you think about it, we want the derivative of t. Well, we have the equation of t. We're taking this with respect to d. Our only variable in here is d. So this is actually just like 3.7, and I'm doing this so we can differentiate between the two, between 3.7 and 3.9. So I just simply need to take the derivative of this equation to get dt dd. So taking the derivative of the left, we have dt dd. Moving over to the right, c over 2 is just a constant multiple. So I'm just going to write that constant multiple, c over 2. The derivative of d cubed we treat like normal because the d's here match. So it's just a regular 3. So the 3 drops down. We have 3c over 2 for that, times d squared. Minus, again, we can use the power rule on this. So we'd have a 4/3 d. All right, so at this point, we've taken the derivative. Again, that was pretty nice because we just had two variables to work with and we didn't have to use implicit differentiation or anything like that. Okay, so next follow-up question is for what doses does the temperature change increase with dose? Okay, so first keep in mind we're thinking about temperature change increasing, or in other words, change increasing. So recall that change in temperature from what we had before was dT dd, that is the change in temperature, right? And now we're asking increase, okay, get larger. So if a derivative is increasing or getting larger, we know that that really means it's positive. So what we're looking at is 3c over 2 times d squared minus 4/3 d cubed, and that's just dt dd that I found before. I know I want this to be positive, so in math terms that would mean greater than 0. Right, so now we keep in mind that the question asked for what doses does the temperature change increase. Okay, so if we want doses, remember in our equation doses was represented by d, so we need to calculate, aka find d. Right, we have the second part of this set up. We know we have that rate of change increase by the equation, so now I'm just trying to find d. So if I just solve this equation, I see I can factor a d squared out of both of these terms. So I have d squared times 3c over 2 minus 4/3 d is greater than 0. All right, thinking about this, okay, we're going to get two solutions because we have a multiple here. So we get d squared is greater than 0. Well, we know this is always true. D squared would mean that d is always positive. Therefore, we know it's always true that the d squared part is greater than 0, meaning that's not really going to impact this being positive or negative because it's already positive. So basically, since this is positive, there's no way we can get a negative out of it. So this is just always going to be true, which means we don't have to worry about it. Okay, what we do have to think about is the second multiple here. So that would be 3c over 2 minus 4/3 times d being greater than 0. So what we need to do is solve for d here and ensure that this is going to be greater than 0. So solving for d, I'll subtract the 3c over 2 to the other side to get 4/3, negative 4/3 d is greater than negative 3c over 2. Now I'm going to divide the negative 4/3 over. So I have d is, and then remember from algebra, if you divide by a negative, you have to flip the inequality. So I have d being less than negative 3c over 2 times negative 3/4. All right, and sorry, this is a little messy, but coming up here, that would mean that d is less than 9/8 times c. All right, so we basically just need to make sure d, the dose, is less than 9/8 times that constant c. All right, so like I said, this one is a little bit nicer, a little bit more gentle because we only have one variable in it. But what we're going to see is when we have related rates, we might have multiple variables that we have to work with, and we may not always just be given the equation. Okay, so I think you could probably guess based on our work in 3.7 that 3.9 is not going to be something that you can just memorize and work through, or you do the same thing every time and you don't have to think or work hard with it. I think that's probably pretty clear. So what I'm going to do is do my best to give you a process to follow when you go through these, so sort of a thinking process, right? You need to follow this. So that one of the biggest mistakes I see students make when they try to approach these problems, they just kind of read it all at once and go for it. You need to think about it a little bit more, peel it apart a little bit more, and actually write out what's going on. It might seem like more work to do that at first, but once you do it, it gives you a process, it gives you a thinking process, and it helps you see, I should say, it gives you a procedure and a thinking process, and it helps you see where you need to go with the problem. So you do need to write that out. And honestly, let's say you do one of these on an exam and you get stuck and you don't know what to do, if you at least write some of the steps out, you get yourself some partial credit, so you shouldn't be thinking only in terms of scores, but if you are, that's a good thing to keep in mind. Okay, so a process for this, the first thing that I suggest doing is going through the word problem, peeling it apart, and identifying all the quantities that you know. So whether those be related rates or other info, identify everything you know and everything you're trying to find, or I say everything that you want to show. All right, after you do that, what you want to do is establish a relationship between those things, a relationship between what you know and what you want to show, aka some equation. Right? Next, you're going to do implicit differentiation with respect to whatever the independent variable happens to be. Oftentimes it is time, but it's not necessarily true for every problem. All right, and then after you do your differentiation, then you'll go through and substitute all of your known quantities in and finish solving the problem. All right, so we'll start with a fairly simple example, and I will also tell you that the notes will kind of build up in complexity. You are going to see really tough stuff in your homework on this, so lots of stuff that reaches way back into prereq knowledge. It gets tough, so you're really going to need to leave time and ask questions. All right, so first example with the related rates question says, a pebble is thrown into a pond and it causes a circular ripple. The outer circle radius increases by 1 foot per second where r equals 4 feet. Find the rate of change of area. Okay, so first, let's just kind of think through the logic behind this. Right, a pebble is thrown into a pond and it causes ripple. I think we could probably all envision that. If you throw a pebble into a pond, into some body of water, it's going to ripple out in a circular form. All right, given information says the outer circle's radius increases by 1 foot per second when r is 4. All right, so this is a piece of information that we know. I'm going to write it down. I need to do that in math terms. So it says the outer circle's radius increases, and I see that 1 foot per second is a rate. So the rate of the radius increasing is dr. I see that the units on this are seconds, which means that this is with respect to time. So I know dr dt is equivalent to 1 foot per second when r equals 4 feet. Okay, so we put a little check mark next to that. We wrote that down. We've pulled out that given information. All right, the question says, find the rate of change of the area. Okay, well, that's what we want. So what we want is the rate of change of area. So we want to find, I'm going to color this differently. Find, aka what we want, the rate of change of area. Right? So if you think about that, the way we'd write rate of change of area in calculus terms is dA, the change in area, dt, the change in time. All right, so now we've peeled apart what we can out of this question. We have to work with it. So we've completed step 1. We move on to step 2, and that is we need to find an equation that relates these two rates. So we need an equation that relates my two variables, which are a and r, that relate a to r, the radius, area to radius. Right? So if you remember some prereq skills, we're talking about a circle here, so you essentially just need to remember what the equation to the area of a circle is, and that is a equals pi times r squared. All right, now we have that equation that relates our two rates, so I'm going to go ahead and take the derivative. Right, looking on the left-hand side of this, I'm taking the derivative with respect to t because that's the rate of change that I'm given here. Those are the units I know I'm going to end up needing. So the derivative of a with respect to t is dA dt. Okay, this is equal to, pi is just a constant multiple, so I'll rewrite it. All right, now if you think about the r squared, I need to take the derivative with respect to t. So I can't just write 2r there, because I need to use implicit differentiation. So when I do that, I'm going to apply the chain rule. R is like my little inside function. The squared function is my outside function. So the derivative of the outside is 2r, technically to the first power, but I still need to multiply by the derivative of the inside, which is dr dt. All right, so for me, when I get to this point, I think, oh, awesome, this is really good because I have the rate that I want in here. Okay, I want the dA dt. I have the dA dt. That's a good thing. Okay, secondly, I have the rate that I have. I have something I know about in here. So that would be the dr dt. So when I look at this, I think, okay, this is good because I have these two rates that I'm trying to work with after I've taken the derivative. All right, so from this point, I'm going to go through and substitute in the given info. So substitute given info. Okay, I know that dr dt is 1 foot per second, and I know that r, or I want this, or had that when r was 4 feet per second, so I'm going to plug both of those in. So I have dA dt being equal to 2 times pi times my r is 4 feet, and dr dt is given as 1 foot per second. Right, so that's equivalent to, we have dA dt equals, let's see, 2 times 4 times 1 is 8, so we have an 8 pi feet squared per second. Right, one really good way to check yourself on this is units. I will say sometimes the problems get so complex that to write the units in throughout gets a little complicated, but if they're simple enough, you can check with them at the end. If it's not very simple, it's really good that we have this Leibniz notation because that tells us exactly what our end unit should be. So here, our dA is really the change in area, and we know the units of area are squared. So we would expect this to be in feet squared. That's exactly what we have, which is good. Time was expressed in seconds, and we got seconds from our calculations, so that's exactly what we would expect. It's also a good thing. All right, so like I said, this one's a little bit more simple. These will get more complex. In the next couple of videos, I think I recorded them on a snow day, maybe last quarter. So if I say anything about a snow day, anything like that, please just ignore that, but pay attention to the actual content in the video. Thank you.